Hi everyone. A little correction at the end. It's not entirely about Android. You can use the things I will be talking about anywhere, basically. So, I'm Mateusz. It's good to be here. I'm first time here. And I will try to keep it straightforward because the subject is pretty complex, I think. So, you join your first company, or maybe this is your fifth already. You are starting to get familiar with the patterns used, with the code base, and everything looks incredibly thought out. Or maybe not. And on the other end, you are trying to get to know how did they do the things, why did they do them this way, and you start to get states that should be impossible. The project grows, the number of developers grows, and because of these reasons, the architecture evolves, and we get new patterns that try to limit the amount of decisions that developer has to make, just to limit the amount of mistakes the developer makes. And because of that, I would like to get you familiar with one more pattern that tries to limit the amount of decisions of developer to as least as possible. Okay, so what's for today? We will talk about the patterns and which one is the best. Why do we need them at all? What is this FSM? How does my dog Henek work? If and when should you use it? And one little bonus. So, which one is the best? Obviously, it's MVC, if you ask, is 2010. Or maybe MVP, if you ask, in 2014, named most vulnerable pattern after crashing on its first demo. MVVM, with its magical data binding on maybe MVI that you already use, or maybe you should use. It's hard to pinpoint 1 year that it started to get popular, but it's slowly becoming like a model of solid architecture for a lot of mobile apps and not only mobile apps. So which one is the best? Maybe the so-called FSM, which is, the full name of it is Finite State Machine, that you may already use, but probably not. What's the story behind? Let's keep it short. It's from academia, from the United States, mostly, let's say, like everything else. Its practice is deeply connected with Boolean logic, automata theory, Turing machines, but that's too difficult for today. So you can watch it after the talk if you are not bored listening about it during your studies. But let's go back to our patterns and focus on the differences between them. I know you are looking, there are some. So what are the differences? There are 3 main parts of all the patterns I listed. And finding the differences can be a little bit like the picture before, because you can use any pattern, but most of the code will stay the same. In every one of them, we need an M, which is obviously a kitchen. Each one of them has a kitchen. It stores the ingredients, it prepares the dishes, it does not know who is ordering, and the kitchen is our model. And we always have the V, which is customer and customers. They say what they want, not always precisely. They receive a ready-made meal. They can't make them themselves, that's important, and they are generally pretty stupid. They just order and consume. And the most important part, our connector, that's the part that adapts to our ever-changing requirements, the part that changes its form to meet the demands of applications. So, our FSM is basically an MVVM, in some way. We still have a view model. The view model is based on a finite state machine. I'm obviously talking about the mobile apps, but you don't actually need a MVVM, but we mostly still use some kind of view model, of course, in case of the screens. But to maybe communicate a little bit directly, could you please raise your hand if you have ever heard of FSM? Okay, that's nice. Please keep it for a moment if you know how to build one. Okay, I have 2 more questions, but not many hands are raised already. If you actually used it in production, okay, we've got 2. That's the highest score so far, I think. So, what is it? That's Hienek, my previously listed dog. Hienek is a pretty simple creature. He has 2 states, and that's the first thing we need to build one. Hienek can be happy and Hienek can be sad, and he's always in one of them. He also reacts to commands. He reacts to come, and he reacts to leave, and that's the second thing we need to build one. These are transitions. And let's keep it simple here. We will go deeper in the next slides. But how does this relate to my app? So let me tell you by building the simplest form of one. So we have the state that I mentioned, and we have a set of events. What will we build? We will build some traffic light simulator. A really simple example, because we can only have 3 states: red, green, and yellow. And we only have 1 event for now. The timer expired. That's the simplest implementation of traffic lights. No cameras, no other stuff, just the timer. And what's the third thing we need? It's a starting state. We always need one. In this case, we will start with red. Okay. We need one more thing, which is the actual machine, the transition function. How does it work? So it always takes some kind of state and an event. We only have 1 event, and the current state can only be one of 3 things. And the result of it will be our new state in its simplest form. So, how does the transition look like? It always has, in a pure form of a finite state machine, a switch case, a when, or any other implementations depending of the language, of that branches out every possible state. In our case, we only have 3, so we will need to handle every event for these 3 states. So how would that look like? Really simple. If the light is red and the timer expires, it becomes yellow. If it's red, then it becomes green. If it's yellow, then it becomes red. Pretty straightforward. The main takeout from here is that we handle every state and every possibility for an event for this state. It's a lot of boilerplate. I know. I like boilerplate. I like being explicit. Maybe someone coded in Java and misses that. That's a little bit like Java. So let's extend it, expand it to show how does it grow. So we get another event, emergency detected. What do? We need to handle the event for every state. So how do we do that? By changing the light to red. For green light, for red light, for yellow light, we always change it to red light. That's it. The logic is pretty straightforward. All the logic branching is separated. So we duplicate the code, but we can have a separate implementation for every one of states. Let's add one more. That's the last one for the example. Resume normal operation. And this will be a bit different. It will still handle all the events, but just to show the different possibility, we will handle them a bit differently by just returning the current state. Which means don't do anything if the light is green and there is a resume normal operation, just don't do anything. It's one of the approaches. You can use it. You can always explicitly tell it what's the new state, but you can also do an else. Which is the simplest form? Let's say you have 10 events. One of the states only reacts to one of them. For the other 9, you can do just else, don't do anything. Which is okay, it limits the boilerplate, but as you may already thought, the compiler won't tell us that we need to handle something after we add an event. Okay, so let's go into why. Why do we use it? with some examples that are closer to production. Case 1, a chat app. We can type a message, edit, reply, maybe even search, maybe do all these things at the same time. I mean, in every app, we need to think about it. How do we handle editing? How do we handle replying when someone is already editing? Can he delete a message by long pressing it after if the user is in editing mode or replying mode? All these combinations need to be handled, thought at, or if they are not, I guess the app may just crash because of some impossible state. We do that. We have to do that in some way, and I will try to show you one of the ways we can model it. So in an FBI, how would that look like? We will start with a list of messages, maybe some loading indicator, loading flag. Maybe we will keep the message that we are replying to, and a null will indicate that we are not replying to anyone. Maybe we need the same for editing message, and if this is not null, it will mean that we are editing message. We need to think what should happen if they are both not null. Should that even happen? Maybe not. What if the app is loading and we have a non-null value in any of this? This again shouldn't happen, but we don't really know. How would that look like in a finite state machine? A bit different, by just separating. In this case, we actually have some data, some in the states. In this case, it will be our message in a writing state. Then we add the loading state, which is our first. We don't need any data, we are loading. After we actually fetch the data, we don't do that in this example, we go into writing with our messages. What with replying? If the user goes into the replying, then we keep the message he's replying to, and only in this state. We don't keep it if the message is already answered. And same with the editing. We only keep the message we are editing, maybe just to retain the original content or something, to be able to cancel the editing or something like that. The events will be shared in our example. We have the messages loaded, we can send the message, we can cancel, we can start replying, and we can start editing, which will initiate the mode and will change our logic when sending a message. It will all become a bit clearer when I show the actual code. And the MVI, the most crucial part of it, handling the actual logic in an on-event method. So we receive a send message. We compose the message from the text we received, and then we actually update our state, our list of messages, with the new message. To keep it simple, the creating message will be shown like this, as it will be reused later. Okay, let's handle other events, like start editing. That saves the message we want to edit and retains the original content. How do we do that? We start editing, so we actually save the message we are trying to edit. That's it. But if we are editing, we need to actually edit the message by clicking the button that sends it. How would that look like? We need our first condition that will check if we are editing message. If we are, we edit. If we are not, we create the new one, like we did before. Okay, that's our limitation for the app. Our logic says that we can only do one thing at the time. We can write, we can either edit or reply. We cannot do the other. How do we handle that? We will need to always check if user is doing something that is not writing, and we will check a lot. And I know you do that in your apps. We need to check for things. These are our safeguards. We try to limit them, but it's not always possible. How can we do that? We can extend our state a bit by adding something like this. That's an example. Obviously, you probably have 10 better examples in your head, or maybe not. We will check if the user is writing, but by looking at the flags, at the messages retained. If he's replying, or if user is editing a message, then he's not writing. Okay, that's straightforward, but it will be used in our code many, many times. How will it be used? By checking if user is writing, because if he's not, we will not let him edit a message. That's one thing. What about replying? Because we have editing, we need to also reply. How would that look like? We have a when in a send message, because we need to do different things in it. It's fine. I don't always like it, because we are branching the logic from, for me in my head, different branches into one event. Because if the user, we are sending a message. If user is writing, we create a new. If user is replying, we actually reply. If user is editing, we edit. And we need to check for the states in other events. It's a lot of thinking. I don't like thinking. I will try to keep it straightforward and branch out this logic into a separate logic branches. Let me show you how. All the states we have in our app: loading, writing, editing, replying, selecting. How do we handle them? For our writing, when user is writing and the event comes, the user sends a message, we actually do the sending. Okay, if user is editing a message, we are in an editing mode, and an event comes, the event sent message, we actually edit. It's the same logic, it's just branched out, and we have a separate implementation for the same event for a different current state. It's more code, but I think it's more explicit, and you can do a separate implementation for every possibility, if you like it. Maybe you don't, I do. And replying. Same code, same reply message, the actual implementation, but separate branch. Okay, that's it. Let me go into a different case, just to mix things up a bit. I work in onboarding in XTB. Our onboarding looks a bit different, but that's a pretty simple onboarding flow. We obviously choose Pro. We obviously deselect that we want to receive notifications. We accept, and it's complete. We have some different states in it. Okay, MVI, name, email, all the data we need. We need current step. Let's say we need current step to be able to revert to some step, maybe for analytics, for UI simplicity, to easily render all the steps, and all the other data, if the email is verified, if the user accepted the notifications, if it's verifying, and how would that look like in FSM? We will just split it into states. It's a bit different approach, because we gather the data, and we only gather the data we need at the step, and we create some helper objects just to keep the previously filled data. So we start by basic info, we verify email, we receive the code, we pass the state from the previous step. We now have a verified email and a name, because we only need that. Then we actually have the profile data, which is all the data from before, with the data field in this current step, and then we have a complete profile. Is it better? Maybe. It's just a possibility for you to show, for a tool to use. And then advantages of this one, I think, will be visible, for example, during testing, because it's just really, really easy and straightforward. And planning this kind of states is also really easy, because you always know that you can only go to one from your current one. The logic is really safe, it's really limiting, but there are not many side effects that can happen here if you go from step to step without some separate flags and other logic. Okay, and complete for the step where the data is already sent somewhere, and we only need to show the screen that the onboarding has been completed. And the shortest example with a video player that would show where I would not go for a finite state machine. Here we have some data like the position and the duration of the video. So the current position of the video we are watching in like milliseconds, the duration in milliseconds, if it is playing, if it is buffering, how much is already buffered, the quality, if it is ready, if it is finished. We've got a lot of flags. What do? Obviously, we wrap them in some sealed class, sealed interface, like the playback. How would that look like? Maybe like this. And I would stop here. I would not go for like pure finite state machine, because I think it would be not helpful, and we will need to pass all the position, the duration, and the data in between the states, which is not a good example for that. Just to show that it's not always the best option. So were these productions ready? Examples ready for production? I don't think so. What are they missing? They are missing some side effects. We always have side effects. We load some data from the network. We do some queries to the database. Things happen at the same time. They need to happen somewhere. How do we handle that? So currently, what did we do? We had a state, we transitioned it by some kind of reducer, and then it resulted in a state change. The reducer produced our new state. How do we extend that to actually handle some logic? Our reducer can do more things. It can decide that the event that happened may need to run some code. And besides changing the state, it will run some code. What do we do next? Their code finished. It succeeded. It sends an event. The communication is purely through the events. We send another one to the reducer. And reducer can again decide that we only need a state change, or maybe we need another code to execute. We can use these two possibilities, and that's the example of an implementation. But that's abstract, that's concrete. We request a search. Start from content, so our basic state. We search for something. It goes into the reducer. Reducer decides we are showing loading, but we also need to perform search. Okay, the user sees loading, we perform search. We receive another event from the search, which succeeded. The repository was called here. Here happened all the logic, all the coroutines in Android, all the thing you have in iOS, and the search succeeded. We go into the reducer, and it decides that we go to content again. Is this simple? I think it is. We go from content to loading to content. That's the state user sees. That's our state machine. It's always in one state, and we always know to which states we can go from this one. And we've got events, and we only communicate through them. There are two. There is search requested, and there is search succeeded. Both go into the reducer. The reducer does everything here. But the logic is split into separate clear branching. The complete example is here because it's a working app with a gallery that loads images that works in pure finite state machine. There is a link at the end, so no worries. And some parts of the code simplified for presentations. For the nerd that needs to see the whole code, it's in the repository. So we process the event, the crucial part of our machine. We have a reducer that actually calculates the transition. It may want to run some update state. We don't always want that, it's inside this method, but if we have a new state in the transition object, then we update the state. We may want to run some side effects. I will show the implementation, no worries. But we may want to run some side effect code. How do we do that? That's our data logic, let's say. We handle all the side effects, all the effects here. For example, we perform search, we call a repository. We browse images, it goes into a network, it returns some flow, so we've got the coroutines, asynchronous code. And if it succeeded, it's simplified implementation, we send an event that it succeeded. Okay, the event obviously goes to the reducer, and for the people that need to see the actual implementation, it's over-engineered because I've used something like this. that the transition can be a state change, it can be effect, it can be both, it can be none, and sometimes one of them is null if it's an effect. Basically, it's a class with two nullable fields. You can simplify that. You don't need to do the sealed interface. I really like it because it looks really smart, but it's a class with two nullable fields. And sometimes we may want to update state if it's not null from our transition, and the same for the side effect. What about testing the finite state machine? What do you think? I think, like with every other pattern, architectural pattern, it becomes easier and easier. If we actually think about our machine, our state, and our transitions, we create an actual graph with our states, with an actual arrows that will show where can we go. Can we go from content to loading, maybe to some other state? Then we will have a complete tests that actually cover all the possibilities. For our traffic lights, we check. The light is green. Will it transition to red if emergency detected? And we can do that for everything. We can have a lot of states, a lot of events, but still, let's say we have like 10 states, it's a pretty big screen or creation, and like 10 events. It's still less possibilities than with some kind of flux and mixed states, where you can have thousands of possible outcomes. Here, you really limit that, and you will see it if you look at some codes that use finite state machine. So the testing is pretty straightforward, and the benefits are that every transition is testable, the whole business logic is explicit, you know what can happen, and we write it in our code, transition from red to green. I know it won't be this simple in a production app, but it still be pretty straightforward if you design it well. Okay, no hidden state combinations, because everything is explicit. And it's easy to verify completeness if we tested everything. What are my conclusions? Setup overhead. What do I mean by that? There is a lot of boilerplate. I know. I like boilerplate, as I said. But the maintainability is great. It's really easy to extend. If an inter joins the company, the team, it's really simple to follow the logic. If the same inter joins and sees MVC, MVP, or some older pattern and has to know that some kind of flags connected with each other means something, it's not that easy, trust me. Best for complex flows, arguable, but if you see a lot of flags that you need to be used together, maybe it's a good place to think about this pattern. Overkill for simple screens, sometimes, because there is a lot of boilerplate. And the learning curve, in a way that you need to start thinking in states. Because if you do it wrong, and if you choose your states wrong, there can become a lot of them. And it's not easy. It's not going to be easier than just using the pattern that you know well. So there is a little bit of learning and a mind shift required. And what can you do right away? Start thinking in states, maybe. Look for complex flag-based logic and try to model your next screen as a finite state machine. Thank you. There are 3 QR codes. There is one positive with the repository. There is one neutral with my LinkedIn, and there is one losing with a YouTube link. So choose wisely. Thank you. I'm ready if anyone has any questions.
Okay, thank you for your talk. I have a question regarding long-running side effects. How can I cancel a side effect in this case?
Yeah, that's a good question. How do you cancel long-running side effects? It's your decision in a way that it's not connected with a finite state machine at all. In the repository I linked here, I'm using one channel for all the events that are done sequentially, and the effect is actually need to finished with all the side effect logic that is not running on the UI thread, but needs to finish before we go to the next one. But you can decide. You can have another channel, another coroutine thread that handles these side effects, and the order of them is up to you. I mean, it's not dependent of your architecture. You just have a loop of events, and you can do it however you want. Does it answer your question?
Yes, thank you.
Thanks for the talk. Enjoyed it. I have a question about state modeling. So in case of your chat example, I'm wondering how would you model states for seemingly exclusive states, but sometimes they can happen at the same time. For instance, you may be writing a message and loading messages at the same time, and you don't want to lose your message that is being written right now.
Okay, that's a good question. I need, what two things do you need to do at the same time? Because I didn't catch that.
So you modeled the states to be mutually exclusive. So
Yes.
loading cannot happen the same time when you have writing or replying. But in real app, you would have some states that can happen at the same time, like writing and loading, and maybe editing a message that you just open in line, things like that. So how would you have essentially unions of states, if that's possible?
Yeah, you can have a hierarchy here. I did not do an example like that, but you can do many state machines if you really need the operations to happen at the same time and do not have any race conditions. And there can be a separate machine with separate writing mode or a separate instance next to our finite state machine. I mean, we are in the mindset, I think, of the MVI where there is a single state. We don't have to do that. And if we have clear states from our, for example, 2 or 3 state machines, it should be still pretty easy to handle all the possibilities happening. That's one thing. The other possibility is don't do finite state machine. And sometimes it's not a good choice. Yeah, I think that's it. We can talk about it a little bit more because it's a hard question and it's always needs a bit of thought to actually design it well. But thank you.